Well, hey there, chemically inclined. It's time to talk about Le Chatelier's principle and the idea of how different variables such as concentration, temperature, volume, and pressure can affect what a reaction is going to do. Basically, get the universe to do what you want to do. So we're going to target with that today, of course, is these little monsters. Oh, look at all those wonderful plants. I wonder how you have so much fertilizer to grow those plants. Don't worry, it has nothing to do with this, just real life. Not just chemistry. Here's a simple reaction. We got some carbon monoxide slamming into some oxygen gas, and it can make or break CO2 gas and give off energy. I want to know if I made all those different shifts, what would happen? And then you should also be able to explain why those shifts would occur, right? Cool. Pause it, write down the question, try to figure it out, and see if you know this stuff, and then we'll try it together. Awesome. Warp speed into the next part. Going to get rid of my big ugly head. If we look at this, first thing I think about is I always think about energy, right? So if we look at this reaction that's right here, first thing I'm going to do is I'm going to turn it into an energy diagram. If I keep that simple, right? Here's my energy. There's my reaction coordinate over time, basically what's happening. And I got these things called reactants over here, the carbon monoxide and oxygen gas. And then I got these products over here, which is CO2. And, I can cheat and say that energy is my product because it's on the product side, right? So if I look at this, is this an forward reaction? Is this an uphill or a downhill battle? Well, energy's coming out, so that means that is being released. So that means that the forward reaction, is a downhill battle, or what we could say is it's exothermic, right? But we know that all reactions can go both ways, so if I look at the reverse reaction, that requires more energy, activation energy to get in. That's what this energy is for, so that's the endothermic reaction. Always think about the energy first. Now I'm going to change some things. In the first one, I'm going to add more CO2. And I can see that right here, CO2 is one of my products. So what's going to happen to the reaction? Well, if I add products, it's going to shift to favor the reverse reaction, right? And I'll just draw the arrows for the shifts, or we could say that it favors is a good good term that we use in chemistry, right? And why is this going to do this? Well, simple. If I add more of these products in, the CO2, that means the CO2 is going to do what? It's going to collide more often. This is going to increase the number of collisions of my product, right? The CO2, which will then cause it to shift to make more reactants, right? This is because this is going to collide those reactants more often. That's too many product collisions. And when those products collide, they turn into reactants. Hey, that's Le Chatelier's principle, which is what we're talking about here, right? And Le Chatelier's principle is all about this idea of collisions. And collisions for a reaction in the universe represent stress. Le Chatelier basically figured out that if I increase the stress of a system, I put stress on a system, the reaction will do whatever it takes to relieve that stress. I have too much stress from too many product collisions, so it destroys the products that make more reactants. It's elegant, right? Oh, or you just simply think, if you add, it moves away, hein? C'est ça français. Now, if we look at this, now I'm taking, and I'm going to take away CO2. So what's it going to do then? Well, that's going to cause it to favor and shift towards the forward reaction, right? This is because if I take away the products, it's going to decrease the number of collisions of those products. The CO2s aren't going to run into each other enough. Now, what that means, of course, is this is going to shift it. This will shift it to actually favor the reaction to make more products. Basically, the universe is like, hey, there aren't enough product collisions. There's too many reactant collisions. I've taken the products out of the way. Now the reactants can collide and make more of the products until it reaches equilibrium where it balances out. So this will temporarily shift it, right? To make more of those products. Hey, I can take it out. Third one, right? I'm going to take away oxygen. Well, if I remember Le Chatelier, add away, take towards. Well, oxygen is one of my reactants. So basically what I'm doing is I'm going to shift this thing to favor the reverse reaction, right? What I'm doing here is I'm reducing the number of collisions of my oxygen, my reactants, which is going to shift the reaction to make more reactants, make more oxygen. I took the oxygen out of it, so it's not colliding with CO, right? Which means it's more likely to have collisions with CO2 because it's no longer in the way, and that's going to then shift it to favor where I took away. It moves towards, right? That, of course, you should notice all of those changes were changes in concentration, and they can shift it temporarily because basically you're changing how many things are colliding, which reactions are all about collisions. If I look at number 4, it's a different story. I'm adding this stuff called heat energy, right? So key thing I can do is I can think about energy, if I want to keep it simple, I can think about it in terms of just a reactant or a product. And in this case, energy is a product. So if I add, it moves away, right? So this is going to favor the reverse reaction, right? But the reason why is more elegant. Basically, what I did was I increased the amount of heat energy. And heat energy basically makes things move faster. If they're moving faster, that means they're going to collide more often. They're going to slam into each other more often. And that stresses out the universe. But this is going to increase the collisions on both sides, right? They're all together. They're all mixed together. So don't have the misconception there's some magical pickleball wall. They are connected together. And if there's going to have too many collisions, the universe is going to be like, whoa, that's way too many collisions. So what it's going to do is I added heat, which is one of my products. That's going to favor always the endothermic reaction. Because basically what's happened is there's too many collisions. So what's the reaction going to do? There's too much energy, kinetic energy here. So it's going to store the energy in bonds, in chemical bonds. And that's going to ultimately reduce the number of collisions. Hey, I stressed the system. I made it have more collisions. The universe is like, hold on, buddy. Now you're going to have less collisions by storing the energy inside of bonds and holding the particles together. Quite elegant, right? And then it reaches equilibrium. Now, if we look at number 5, I'm going to take away. I'm going to take away heat. I'm going to chill it down, right? Well, that's easy, right? If you think about it, if I take it moves towards, I'm going to take away the heat, which means it's going to shift towards it. Predicting where it'll go is pretty easy if you keep that simple rule in mind, right? But basically what I did here was I decreased the amount of heat energy. And if it's moving slower, then it's going to collide less. It's going to decrease the number of collisions. And that will always favor the exothermic reaction. You can see that I took the heat away and it shifts towards the forward, which is the downhill battle. Now, why it does that is a crucial thing. This reaction is now shifting because in this case, I'm going to break bonds to release energy. And that releasing of the energy is I reduced the number of collisions because I chilled it down. So it's going to break bonds to release energy to increase the number of collisions back up to keep the number of collisions at equilibrium. Hey, that's why we call it equilibrium. It's about balancing out the number of collisions. You can see with 4 and 5, what I'm changing here is I'm changing the amount of energy. And heat's usually the typical one that we use because, it's simple to add or take that away. But you can do this with light. You can do it with UV. You can even do it with X-rays and stuff like that. But heat is the one that we're primarily involved in, right? Endo-exothermic. Number 6 is a different story and far more fascinating. I'm going to add pressure. Now, we've already learned about pressure this year, right? So let's think about what's going to happen. If I add pressure, what is pressure really? Well, pressure, as we know from the gas laws unit, is really just the number of collisions per unit of time. So if I increase pressure, then really I'm increasing the number of collisions, right? If I increase the number of collisions, then the reaction will do the exact opposite. It's kind of like teenagers, right? If I try to force it to do something, it's going to do the exact opposite. That's why teenagers are the way they are. That's why all people are. So if I increase the number of collisions, the reaction is going to shift to do what? To decrease the collisions, because that's the beauty of the system, right? Now, if we look at this, what that means is the reaction is going to have to shift to whichever side has less particles to collide, right? So that means that if I have less particles, I have less collisions. And if we look at what we've got going on here, we've got on this side, the reactant side, we've got 2 of those carbon monoxides and 1 of those oxygen molecules. On the other side, we've got 2 carbon dioxide molecules. So which direction is going to favor? I made too many collisions. It's going to favor the side with less particles. It's going to shift towards the forward reaction. It's going to shift the side that has the carbon dioxide on it because that's less particles, so less collisions. I have 3 gas particles versus 2 gas particles. So whichever side has less particles, if I increase pressure, it's going to shift to make more of those things. Cool. You can see that we can change the concentration, we can change the amount of energy, and we can also change the pressure. And there's something that we learned in gas laws that is, well, basically it's inversely proportional to the pressure. If we want to affect the pressure, the other thing we can affect is volume, right? That's why it goes right next to it when we do it, P times V in Boyle's law. So if we look at this, volume is another way that I can change that thing. And a good way to think about that would be like bumper cars, right? If you get into a bumper car ring and there's only like a couple of cars, there's lots of space and you don't run into each other as much. There's less collisions. I'm decreasing, of course, the number of collisions because I increase the volume. They're inversely proportional to each other. Likewise, if you go into most bumper car rings, they're pretty small in their volume, so that's going to increase the number of particles. Now, eventually, if you've added too many different bumper cars in there, they're going to collide so much they're all going to get stuck together. It's like they get bonded, and that would decrease the number of individual particles, which would decrease the number of collisions. Not that this has anything to do with real life. It's just that reactions are collisions. They're bumper cars. Soup them up, and you could have real cars in the bumper car ring, and now you're actually making and breaking bonds, right? So just think about bumper cars and the amount of space that they have, and all that stuff we learned back in gas laws. That's why we learned about particles first. Now, let's see. Normally, we go after TLW 17.15 because it's got some good stuff, and Le Chat online where you played around with things like concentration and heat and all that stuff. Let's see if you have actually grasped of that stuff. If we look at this, it says, what would happen if you added energy using the heater? Well, if I look at this reaction, we can see that, the forward reaction is an uphill battle. So that means that the forward reaction is something that requires additional heat. So I'm adding a reactant that's going to favor a shift to the right. That's going to help to raise this total energy line so that we can get over the hump to the actual product side over on this side. So I added heat. It moves away. Le Chatelier. If I look at the second one, it says, what would happen if you added AB? Take a moment. Think about what it is. Cool. AB is a product. So if I add more product, what's it going to do? I'm going to have too many product collisions. That's going to shift it away from it. Oh, that's going to shift it to the left to destroy product because there's too many product collisions and decrease the actual collisions of those products. Hey, this is easy. Le Chatelier, add away. What would happen if you added energy using the heater to this reaction? Well, first thing you want to think about is energy, right? And if we look at this, these are my reactants, these are my products. Is this an uphill or a downhill battle in the forward reaction? Well, neither. This is a weird reaction where it's equally energetic to make both of those things. We can see the total energy is there. So it says, what happens if you add energy? Well, it makes it easier for them to go back and forth just as easily because they both have the same amount of activation energy. Now, what this means is there would be both reactants and products that would have more energy, but the amounts wouldn't change because it's just as easy to make or break either. So this would stay at the same concentrations, but it would certainly do it faster, right? Now, fortunately, most reactions, in fact, all of them don't occur like this. There's one side that's favored that's a lower energy potential, but it's a good way to make sure that you understand what's going on with activation energy. Now, typically what we would do in this day is one of the coolest labs. It's called the concentration effects lab. Kind of makes sense when they call it that because you're seeing what the concentration affects. We'd use this cool stuff called potassium thiocyanate. The S is the thio anytime you have a sulfur in those things. And you would take that stuff and you add it to stuff called iron nitrate. And if we look at that ferric nitrate, right? This one's actually iron 2+, so this ferrous nitrate. It will create this red stuff called iron thiocyanate 2+ ions. And the cool thing about it is when it makes this product, it turns red. It's a red that you can see, and it will stay in solution, changing the solution to red, but it will still be at an equilibrium. And the amount of red that's there tells you how much iron thiocyanate is there versus the iron nitrate, right? And these are my reactants, and that's my products. Now, to look at it in terms of a reaction, if we wrote it as a complete ionic equation, we can see that we've got iron ions, 3 pluses. We've got some some nitrate ions. We got some potassium. We got some thiocyanate. They will smack together and make this new stuff called iron thiocyanate, right? And they will, of course, have spectators like potassium 1+ and nitrate ions. When all those things go into this reaction, because we're simplifying, we're not showing all the coefficients, there would be 5 different changes you would basically do with the lab, which we'll look at next class when we explore these things to understand Le Chatelier's principle, which is really what the concentration effects lab is about. Now, you normally go after that. You're going to have your weekly assignment this time, and the equilibrium test will be coming up in 2 days. The PCL5, of course, will be a normal assignment as well. Our target today was to make sure that we understood how changing concentration, temperature, and volume and pressure could affect what the reaction will do. It's pretty easy if you think about Le Chatelier. And Le Chatelier is all about, of course, stress. And stress in reactions comes from things like collisions. If I increase the amount of stress, I increase the number of collisions, so the reaction is going to do the exact opposite. The other trick is to remember that if you add, it moves away. If I add reactants, for instance, they collide more often, and it will destroy those things to make more products. If I take away products, right, that's going to, of course, decrease the number of collisions, and that's going to favor making more of those products. If I increase the temperature, of course, I have to think about energy diagrams. So let's say that we have a nice forward reaction that is exothermic. If I increase the temperature, that's going to favor whichever side needs that. That, of course, is the reverse reaction. The endo is going to take heat to do that. That's going to favor storing that energy in bonds because you've made, of course, more collisions is too many collisions, so it stores it up in these things called bonds. That's why it has higher potential energy as a reactant. And then with volume and pressure, it really comes down, of course, the number of collisions, which can be affected by the number of particles. If I have one side that has more particles, right, and I increase the pressure, they're going to collide more often, so it's going to shift to have the side that has less particles. And less particles means less collisions, right? I can also affect that by taking it and putting it into, oh, I got a big space, oh, I got a little space. It's going to favor making less particles so they collide less often. So that means that we can play with all these variables to get reactions to do what we want. Le Chatelier is a wonderful principle if you apply it and if you understand that it's all about collisions.